Hello students. Today I want to talk with you about motion. But in order to do that, we need to talk about forces, because forces cause motion. This may be the most enjoyable topic in all science. I certainly loved it when I was a student. But there could be a stumbling block for you. In our real world, the motion of particles and objects is complicated because they're subject to many, many different forces, including friction and gravity. Now, if we were in outer space and you threw a ball, it would go almost in a straight line forever. Of course, that doesn't happen on Earth. No matter how fast you throw a ball, gravity will pull it to the ground as fast as it would if you dropped it. It's true. Also, friction makes everything in our real world go slower. Let's look at the two classes of forces, and we'll try to sort these things out. We have contact forces and forces that act at a distance with no contact to the object at all. There's tension when we pull something, friction when two objects slide against one another, pressure when we inflate something like a balloon, and the normal force, which you may not have heard about before. I'll get to that in a minute. Action at a distance has always spooked scientists. We know that from writings over 2,000 years old that ancient philosophers pondered these matters and were very frustrated not to be able to get good answers. It was only until the last few hundred years where people started to make sense of these matters, and only in the last century did we even attempt to try to figure out what was going on in the nucleus of an atom. You've seen electrostatic forces. This is where when conditions are dry, you shuffle across a carpet and you get a shock. Well, electrostatic forces can be attractive and repulsive. Let me rub on a few electrons to these plastic labels and we'll see if we can't show them. There. Electrons on the surface of these sheets are similarly charged and they're repelling each other. Now, my hand is neutral because I've been grounded. When I put that in there, it's attracted to them. When I remove it, they repel each other again. Not quite so much because I've removed some of the surface electrons. This is the first thing you want to know about electrostatic forces. They can be attractive and equally as repulsive. I know you're all familiar with magnets. This is another force at a distance. See, even through any kind of material, as long as they don't get too far apart, they'll create a force at a distance. This comes from the interaction of electrons inside the magnetic materials. You may be less familiar with magnetic repulsion. Magnetic and electrostatic forces are both balanced with attraction and repulsion. And, as we now know, they really are different forms of the same force, which we call electromagnetism. Nuclear forces only operate at small distances to keep protons and neutrons together in an atom where they would normally force themselves apart. We're not going to talk very much about those, but I wanted to give you a complete list. Then there's gravity. Gravity is a little different than the other forces. It's only attractive. And it's the weakest force of all these actions at a distance. Now you may be wondering, we go through life constantly affected by gravity. We have to be cautious about falling from high places or even tripping and hurting ourselves on the ground. How could gravity be a weak force when it affects us so strongly? Let me demonstrate. This tiny magnet is applying more force to this object than the entire Earth. This is stronger magnetically than the entire Earth is gravitationally. Much, much stronger. You think of how tiny this is compared to the entire Earth. Now, in order to really get a handle on forces, I want to simplify our discussion of them. And one of the ways we do this is with force vectors. So we can draw diagrams. For example, let's do this experiment. I'll take this object and drop it. Well, gravity pulled it down to the tray, but now it's stopped. Why doesn't it keep going? Let's draw a force diagram. There's the marker. Gravity times the mass is pulling it down. The tray is applying an equal force we call normal. When anything is resting on a table or the ground and it's not moving, that doesn't mean that gravity is turned off. It means it's being balanced by a normal force. If the tray isn't there, then it will keep falling until it finds another force to balance it, just like that. Now, there were natural philosophers from many, many hundreds of years ago that considered these actions at a distance. Newton took many of these ideas and clarified them into this beautiful equation that is so helpful to us. Let me read it to you. F is the force, M is mass, and A is acceleration. So the force is equal to the mass times the acceleration. Now, let's be clear. Mass is not weight, and acceleration is not speed. These are elements of our normal daily lives, but we're going into an abstract world here where we're going to be talking about force, mass, and acceleration. say, for example, that you want to know how heavy you are, which is an expression of your body mass. What does the scale do? It uses this equation. You want to know that. Well, the scale already knows what the acceleration is. That's just gravity. When you step on the scale, you apply a force, and the scale measures that force. It automatically divides by gravity and gives you your mass. Now, what would happen if you took this scale into an airplane and flew it at high altitude? It would give you a new mass, because it would be calculating the wrong gravity at high altitude. And if you took this scale into orbit, it would give you a mass close to zero, because, again, it has the wrong factor for gravity. In orbit, there is nearly no gravity. Does that mean your mass is zero? No, your mass doesn't change like that. But gravity does. And Newton's formula for force, mass, and acceleration allows us to do those calculations very, very simply. Now, if we want to know how a vehicle will accelerate, we can rearrange the formula like this. Here we want to know about how fast it will accelerate. Well, we have two factors to take into consideration. If the mass is heavier, then the acceleration will go down. If the force is greater, then the acceleration will go up. This is why people try to keep building cars with more powerful motors that weigh less. Less mass increases acceleration. More force increases acceleration. So this is the element of inertia that you'll hear about. In fact, a century ago, scientists did not use the word mass. They called it inertia, which is a property of mass. It resists acceleration. As inertia goes up, acceleration goes down. It's harder to move something. And you'll see a demonstration of this in the lab that I prepared for you. Watch that video and see how more mass decreases acceleration.